companies which subscribe to their collision avoidance service are based on linear covariance propagations. What is provided actually is the covariance of the position. So, while the previous part in some sense was also applicable to space debris, what I'm saying now is only for asteroids. So let's suppose you know what the line of variation is from the previous lecture. Let's define what the problem of impact monitoring is. First of all, let me give the definition of virtual impactor. A virtual impactor corresponds to a possibility of impact in generic terms. To give a specific mathematical definition, for a given known asteroid, a virtual impactor is a connected set of initial conditions leading to an impact at about the same date. Now, why we require that it is connected? We can have sometimes two separate virtual impactors, that is, two separate connected sets, corresponding to an impact even at the same date. But they go through two different dynamical routes. Like one passes through 3 intermediate encounters with the air, the other one through 4, or something like that. So through different clusters. Impact monitoring is a procedure by which the VIs, which are compatible with available observation, that is, the ones over which the probability density function is not negligible, in such a way that the probability integral over the initial condition corresponding to the I gives a number which is meaningful. What means not meaningful? In operational impact monitoring, we normally consider that the probability of 10 to minus 11 is negligible. Minus 11, 10 to minus 12. Again, this is a little bit subjective, but this also corresponds to how computing power. In practice, impact monitoring is possible only for a finite time span, that is, as an example, 100 years, and for impact probability above a given generic completeness limit, as an example for God. This is then minus 7. Probability of 10 to the 7 is not visible. These two values are currently used by the operational NeoDis system, the one in Italy. The method used by both the NeoDis impact monitoring system and the parallel JPL Sentry system is based on LOV searches. What is a LOV searches? The principle is comparatively simple. First of all, we select the finite segment of the line of variation corresponding truncated to some sigma or chi-square value, that is a segment along which the increase of the standard deviation of the vehicle with respect to the nominal solution is not very large, it's statistically possible, and we sample it with a finite number of points. Practically speaking, a few thousand, like I think we currently 2,400 points. And this one we call virtual asteroids. What is a swarm virtual asteroid? Many asteroids replace the only true asteroid. One of these is similar in its orbit to a real asteroid, but we don't know which one. This is also sometimes called multiple hypothesis testing. That is, instead of having a single solution, we have multiple solutions and we try any one of them. Then, given this sampling, we propagate by numerical integration each one of these orbits for, let's say, 100 years. With the orbit, we also propagate the equation of variation, which gives us for every time the state transition matrix, which is the derivative of the current state with respect to the initial conditions. For each of these orbits, at each close approach to the Earth, we project on the target plane a trace point y with its partial derivative with respect to the initial conditions. So if you imagine you have 2,000 orbits, propagated for 100 years, we obtain 20,000, in some limit cases, maybe 200,000 close approaches. And we keep a record of all of them. It's a file which contains all the close approaches. This close approach is represented by the target plane vector with derivative. Now, the first question is this enough? Or to say it in another way, how many sample points you actually need to use is the resolution enough? I will measure the resolution. To do this, we have I need to stress something which I said already, that in reality, we speak of a target plane, but in reality we use a finite disk of a given radius, which we call capital B, on this plane. Practical value is in this range. Now, if you ask why, well, if you have a disk of radius more than 0.23 AU, you would have that Venus as a counterpart to the Earth, it would be difficult in deciding whether the reference was approach to the Earth and to Venus. So the disk cannot be too large, otherwise things still happen.
But why the lower?
Well, if you decrease the diameter, you lose resolution. So it's possible to use the largest possible. But on the other hand, you have more problems of non-linearity in a larger plane. So it's a trade-off which is a little bit difficult. As you will see when we do the computation with Probabilistic. Now, this is the result of the procedure I'm mentioning with one superevent. First of all, each one of the red points is the trace of one virtual asteroid, one particular target plane. These are two separate examples, two different asteroids, two different epochs, so it doesn't matter. This is just an example. There is one, so you see, this is an example, a point, these are points. Now, what is the meaning of the dot of the dashed lines? The dashed lines join two virtual asteroids which are consecutive on the log. That is, if they are the two extremes, I partition the log in segments. If two virtual asteroids are the two extremes of the same segment, so they are k and k plus 1, so I just count them, then I join them by a segment. What's the meaning of this? Now, you have to think that the point of view, which is similar to what is in these days called manifold dynamics. As a matter of principle, the Riemann relation is a manifold with a differentiable structure, and it exists as a continuum of points. We are sampling it as represented by a finite number of points, but we are allowed to interpolate. So potentially, the intermediate points exist if you only make the effort of computing them. Now, if this resolution is high, we have many points, like in this sequence here, 4, 5, 6, 7, 8, in which there are 8 points on the same target plane, then the shape of this polygon, consisting of segments, is quite close to what would be the image of the log if I were to compute it. If I have few points, look at this. This is, here there are 2 points. Just to introduce the terminology, 2 points, the points which are joined are called the return, also train. That is, if a return consists of only 2 points, then it is quite clear that the straight line is not a good approximation of the image of the line of variation. In other words, in reality, linear interpolation is never acceptable. If you want to do interpolation, we need to use nonlinear interpolation. Just to make this comment more spicy, if you look at these points and you imagine that if we had more points, then the behavior would be more or less like the one of the other curve. Not be like this, but would be curved probably quite parallel to the other one. And there is here. So in actual fact, the return which is better is this one. And that shows that nonlinear interpolation is very important. However, in a way, well, this is what we call a singleton, which does not give us much information because it's just one point. So we cannot interpolate in any way. This is another case in which we have 1, 2, 3, 4, 5. Something strange is happening here. Since I think this here we do not have enough resolution, I have taken another example of this phenomenon, and I'm showing this other case here. So you see there are cases, not that the Earth is here, okay? So we have, it's like, I don't know, like in these action movies, somebody is machine gunning the bomb from an airplane, but then instead of having the shots which come closer and closer, at some point, they go away. while it looks like the Earth is going to be hit because this line is going straight in the direction of the Earth, and then it stops and goes back. This is called an interrupted return. And you are trying to do something and then withdraw something. Okay? Now, of course, this is a case in which it's even more true that linear interpolation is not meaningful. As a matter of fact, linear interpolation at this point fails completely because the curve is singular, it's not regular. Why this happens? Well, let's first of all explain why these things are called a return. If something like this happens, that is a single line, instead of giving just one trail on the single target plane, gives 1, 2, 3, 4, 5 separate returns. That means that the line of variation is bent at least 4 times in going up and down in a very complicated way. There is no way to explain how this has happened unless there has been a previous sequence of close approaches which have perturbed strongly the line of variation and bended it in strange ways. I'm not going to explain this too much, maybe Milani will explain a little bit better. In essence, so this must be not the first close approach to the Earth you have between the initial conditions. Maybe there is an impact here, but this impact happens not at the first visit, at the second, third, fourth visit of this asteroid near the Earth. If an asteroid passes twice near the Earth, since the point of minimum distance between the orbit of the asteroid and the orbit of the Earth is a given point in space, that means that both the Earth comes back to the same point, and coming back to the same point means an integer number of years has passed. And the asteroid also must come close to the point, which means an integer number of asteroid period has passed. And then an integer number of asteroid period and an integer number of Earth period must be the same. That means the two orbits are resonant. So this is what is called a resonant return. A resonant return normally adjusts this shape, but sometimes at this behavior. And this behavior indicates that the perturbation introduced by the Earth on the asteroid in the previous passage have failed to reach the critical value which corresponds to the resonance. The maximum perturbation in semi-major axis has not been enough to reach the resonant value. In this example, there was a close approach in 2027. After 5 years, the asteroid has made, if the asteroid was capable of doing 3 tours while the Earth is doing 5, then you would have an encounter which would be very close. But the asteroid falls a little short or a little longer the shape, and then the result is that you get this strange behavior. Well, the theory must be able to handle both of these cases. But let's first finish the discussion about sampling. Let's call S the stretching, which is the length of the vector representing the derivative of the target plane point with respect to the parameter sigma. Sigma is the parameter of the line of variation. So the stretching indicates, well, as the word says, how much a small distance from the space of initial condition has been expanded on the target plane of one of the returns. So the distance on the target plane between 2 consecutive points is S times delta sigma, where delta sigma is the length of one of the segments in the line of variation. We can suppose the line of variation has been sampled with uniform spacing, maybe not, doesn't matter. Let's delta be the spacing, then the distance between 2 points in the linear approximation is S times delta sigma. Okay, if we want to have 2 points, at least 2 points of 2 virtual asteroids give a trace on the target plane, we need that S must be less than d times 4 sigma, delta sigma. I think there should be two. Okay, maybe this computation is wrong by a factor 2, and that doesn't matter. Okay, so if you are sampling with 2,400 points for the interval -3 to 3, delta sigma is 1/400. And then you do a little bit of computation, you get something of the order, the stretching is of the order of a couple of millions radius of the area. Okay, so if the stretching is less than that, then we have enough points. We'll be able to have a return, which is a number of points such that we can interpolate to the possible impact. Now, if you remember that if you have a Gaussian, the maximum, a normal distribution with standard deviation of 1, the maximum value of the Gaussian is 1/√2π, which practically speaking is about 0.4. So, if the stretching is like this, the maximum value of the probability density, assumption is exactly at the center, is of this order. Okay? So this is the way you can compute the probability, which corresponds, and of course the probability can be less, because if instead of being near the nominal, it is on the tail, while the probability density factor is much lower, and you get a lower value. But you cannot get a probability larger than this if the stretching is as large as this one. So this gives you a feeling of what should be the performance of the system if it works perfectly, of course. In the assumption that whenever we have 2 points on the target plane, we have no way to miss one possible virtual arc. Next, up to now we have done nothing. That is, we have done only the same as a Monte Carlo. We have propagated all the orbits one by one. Now we introduce the differential abstraction and we do interpolation. So we have a real curve y of sigma with a tangent vector, which is the one with length s. Then we can find a minimum close approach distance for a given log segment as an example between 2 consecutive VAs. The distance is just the length of the vector y, and the minimum occurs for y perpendicular to the y to the y with respect to sigma. This we call a function of sigma. The zero, now the function f of sigma is smooth, and then we can find the zeros of this function by any iterative scheme, such as regular falsi or Newton. But of course, each of these iterative schemes requires us to compute the value of our function at another point. So we need to be able to perform the iteration. To start the procedure, we just need to find 2 consecutive points. The one with lowest sigma having this sigma less than 0, the other larger than 0. Let's go back. Sorry. Let's go back to this figure. This point, the stretching is going in this direction. Here the distance is decreasing. Here the distance is increasing. So given these 2 points, I can start, you know how regular falsi works. If you have a function which is positive in one point, negative in another point, just draw the straight line, intersect with the horizontal axis, this gives you the next guess. Okay? So by using this, regular falsi has a very important property that is enough to suppose that the function is continuous. Regular falsi necessarily converges towards a point in which the function is 0. The 0 corresponds to the stationary point of the distance, and with a little trivial trick, you can also guarantee that this stationary point is a local minimum, not a maximum. It is possible also to use Newton's method. As I have commented already, Newton's method is much faster in convergence, but has the inconvenience that the theorem says that Newton's method must converge almost never applies. Or, well, applies only if you have hypothesis of convexity, which you cannot practically guarantee in this case. So, in a way, it's better to use regular falsi unless you are very sure of what you're doing. Now, the question is this enough? But this is enough to say I can use regular falsi to guarantee that if there is a virtual impact, I will find it. Now, this is a too strong statement. The reason why this is too strong statement is illustrated by this example. And this is an example of what happens if I have not enough resolution. That is, if my sampling of the line of variation is not adequate to describe the complexity of the topology of the trace of the lobe on the target plane. So in this example, this is the first point, and this is the last point. So let's suppose I had only these two. Okay? Then I would join them with the segment and would think that no minima is going to occur between these two. Because here the distance is decreasing, this is there. Here the distance is decreasing, here is decreasing too. So why I should have a minimum in between? But in reality, the consecutive point of this is this one, and there is this one, this one, this one, and so on. Okay? So you see that there is a problem of complexity. If I don't decompose the lobe into short enough segments, I have no guarantee that the behavior will be simple. And therefore, now what happens if I use, let's suppose I take a point, this point, and some other point like this one. This one, the distance decreasing, this is increasing, or maybe this one. Okay. Here is decreasing, here is increasing. So in principle, I can use regular falsi. The regular falsi will give me one minimum, that is 1, 0 of the function f, and is guaranteed to be a local minimum of the function in the interval between the two. However, in this case, there are multiple local minima. For this local minimum, there is no guarantee that the one I found is the absolute minimum of the distance. So actually, I might have found a minimum, but another min which is not a collision, and then I will decide there is no VI, but there is another minimum which is lower, and then I am getting a false negative result. I get to a conclusion there is no collision at the point. There is a possibility of missing the virtual impact. So what I am supposed to do? What I have to do is to use what we call the principle of the simplest geometry. The principle of simplest geometry says that we can assume that the geometry of the EP trace between the 2 points which are consecutive in our sampling is simple, where by definition of simple, the definition of simple is what is shown in this figure. I have either a simple return, and the simple return is this one, it just passes through as a simple minimum, or this one, that is an interrupted return. Why I can say this? The reason why I can say this is simple. Let's suppose I had the first point here and the last point here. Then, by dividing this distance by the delta sigma, I would judge that the stretching is more. But in reality, the situation is much worse. In reality, the stretching increases, and if, let's suppose I find a collision point which is somewhere in between here. Here, the stretching is much larger than the average value of stretching in this interval. So, to obtain a geometry which is more complex, I have to increase the stretching. Now, the stretching appears as denominator in the probability, because the stretching means that the PDF I had originally in on the lobe, because the stretching is large, the same probability density gets diluted over a larger interval, and therefore the value of the PDF at a single point is much less. In other words, more complex behavior corresponds to actually lower probabilities. Therefore, if my sampling is enough to guarantee detection at a level corresponding to generic completeness, the value of completeness which I have chosen on the basis of which I have computed the sampling. Missing more complex behavior makes me miss the factor which have a probability which is below the generic completeness. Now this is a very complicated argument, and I have also to admit, and I think this is important to know this, that a really rigorous estimate, a real formal mathematical theorem which says we can find every virtual impactor which is above this number has not been proven. And you are welcome to, if you want, to try to solve this problem, because we have not been able to solve it. So it is not true that we can currently guarantee, as an example, to space algebras, if we put the world respect to NAS and Pisa, but we'll find anything which is worse than 10 to minus 7 or 10 to minus 6. There is no such theorem. We do our best, given the computing facilities we have, and given the methods we have developed, but there is no guaranteed result. Somebody says, you must, well, this is a typical definition of requirement by space algebra, you must guarantee that you get Houston factor down to this. The answer is, you try. Okay? If you think you can be done, you try. Now, empirical test of the reliability of our method. This is histogram which contains all the VIs in the Odysseus files. This at the given date was prepared for the PDC. So this is an histogram as a function of the impact probability of all VIs we found, distributed over 400 or so different asteroids. There are tens of thousands of factors. And you see very well how it works. I forgot, this is logarithm in base 10. So it grows until about 7, somewhere here, and then starts declining. The red line corresponds to the generic completeness I have computed, and the green line corresponds to finding only one. So the guarantee of finding one virtual asteroid in the disk. The red line corresponds to finding 2 VIs in the disk. Maybe there is a mistake. Actually, this should be a little bit wrong, but it doesn't matter. So you see the situation is quite clear. Down to some level, which is more or less in the region we are talking about, it appears that we are catching everything, and then it's clear that this decline. Now, to do a more scientific description, we need to use not the probability but the stretching. Because, as I already pointed out, the probability depends upon the stretching, but also the distance from the nominal. Because the exponential decrease of the PDF as a function of the distance from the nominal may result for a given stretching probability which is much less. So if you want to see this reclusion more pure way, you have to use the stretching. Now, the curve in this way looks, again, this is the level corresponding to generic completeness. And this curve here, red curve, is a fit which I've done, and which is this strange curve. Now, this exponent is 0.66. Now, I, of course, conjecture this exponent actually should be 2/3, but if you ask me why, I have no idea. Now, the interesting thing is this other decreasing exponential is this exponential multiplied by the ratio stretching of generic completeness divided by actual stretching. That is, if I assume that for a stretching which is larger than the value of generic completeness, finding enough points in the disk to be able to do the computation of course at random. In other words, it normally happens that we find objects with impact probability of 10 to minus 10. But this is, quite frankly, luck. Okay? So if we are looking for something which has a stretching which is 1,000 larger than the stretching due to generic completeness, means then, roughly speaking, our probability of detecting is 1 in 1,000. If you assume this, you get this curve. And you can see that down to about 10 to minus 8, it gives a full description of the situation. For lower values of the kind of problems. Probably share to do the principle of simplest geometry. The next question is, if there is this relationship, what it is? Is a universal rule which only has to do with the properties of chaos? Is the property of our solar system? Is an artifact of our computational methods? I have failed this idea. So this, I find it is an interesting problem. There is some strange fractal property which is contained in this problem, and I have only a numerical approximation which tells me what is happening, but I have no explanation, no rigorous mathematical theory for this. Still, I think this figure shows that our method performs as well as it should. That is, even if we don't have rigorous formal proofs, nevertheless it works, practically speaking, well enough, because it finds something more or less what it should find. Now, I have to explain, okay, that's on an hour, so I think I have time. I would like to explain, once you have found that there is a virtual impactor, how do you compute the probability? Now, there are fundamentally two methods, actually three methods to do this computation. The first method is one-dimensional. The one-dimensional method is conceptually clear. Let's suppose we have a line of variation. Let's suppose that we know that there is very specific segment, sigma 1, sigma 2, which correspond to the interval on the line of variation, which when you project it on the target plane of one particular encounter, it is inside of the Earth cross-section. That is, the trace of the LOV intersects the disk of the Earth, of the impact parameter of the Earth, along this segment. Okay? Then we can use the probability of being inside the Earth impact cross-section conditional to the LOV. Okay? To use the terminology of probability I've used previously. And this is very simple. It's the probability integral of the segment sigma 1, sigma 2. And this is probability integral that you compute on the LOV. In reality, not even on the LOV. On the segment in the real line of the parameter sigma. So the counter image of the impact in that line is a segment. You compute the integral of the probability density function on that segment. And that's a very simple computation. Okay? When is this way of doing the computation right? Well, I have said that all the points of the target plane are computed with their derivatives. In particular, by using the matrix 2 by 6 matrix of partial derivatives of target plane coordinate with respect to the initial condition, I can compute the covariance in the normal matrix of Y. Therefore, there is an ellipse of confidence. The ellipse of confidence are two axes. One axis, the major axis of the ellipse, has a length which is the stretching. The minor axis has a length which we call the width. Because typically the ellipse is, as I've shown in the figure, is very elongated. So there is a very long axis and a very short axis. The axis, the stretching, is typically so long that actually the tip of the ellipse is outside of the target disk, because value of stretching like 1 million as radii are common. The width is typically small, maybe a few F radii, can be a few kilometers. Now, if the width is a few kilometers, that is a negligible fraction of the radius of the Earth, then the one-dimensional computation is okay. Because I have a line which crosses the Earth. I should do the integral not on the line, but on a strip. And this strip is a very narrow strip, so it doesn't matter doing the two-dimensional integral, I can do the one-dimensional one. Okay. What happens when the width is not negligible. Let's suppose the width is a good fraction of the radius of the Earth, or even worse, is multiple radius of the Earth. This does happen. It happens when the computation, the orbit is poor. When this happens, I should do a two-dimensional probability integral on the circle which represents the impact cross-section by using the propagation of the probability density function to the target plane. Now, the linear probability density propagation is this. Let's suppose, sorry, the coordinates from the target plane are called c zeta. There is a closed approach point which has coordinates cm, zeta m, and there is another point y0 which corresponds to the nominal. Then I should make an integral of this function in which the mean of the distribution of the target plane is the image of the nominal solution. So the mean is y0, that is c0, zeta 0. And then at the point, generic point c zeta, the probability density function is this. W divided is the length, is the standard deviation of c, and s is standard deviation of z. I am assuming I have chosen a coordinate system in which the love tangent is parallel to the zeta axis in such a way that the zeta coordinate is one which corresponds to the long axis, that is as the stretching, and the c axis is the one corresponding to the short axis. This corresponds to a given system of coordinates that we will describe as Now, what is wrong with this formula? What is wrong is that, in general, the point y0 does not exist. If I have an orbit which is not particularly well determined, or a propagation which is done over a long time, in which chaotic effects have increased enormously the length of the confidence region, it may well happen that the nominal solution does not have a point on that target plane, that is on that target disk. Because if the stretching is millions of Earth radii, it's much longer than 0.2 AU. So I can be at 1 sigma, and the nominal should be farther than Jupiter, or even outside of the solar system. So this formula is not applicable because this point does not exist. On the other hand, I have the point, this point, which is the minimum. Then the probability density function at this point, in a semi-linear approximation, should be this one. This is a point on the love. The transverse component is 0. If sigma m is the value of the love, which I have obtained by interpolation, is the value I have obtained through the solution of the value by regular falsi, finding the minimum distance, then the value of the PDF at this point should be this. As a consequence, approximation of PDF should have this structure. Well, yes, there's a small trick. Maybe you have to look at it a little bit to get convinced, but I can guarantee you that it is appropriate. But it's not an exact formula. It's the best linear approximation to the nonlinear situation. It's the best linear approximation which is applicable in a neighborhood of the point yn. Then we do this integral and we compute the probability. That's what we do every day. There is another complicated issue which I will mention only sparsely. There is, of course, another case, the case in which actually the line of variation does not touch the Earth impact cross-section at all. What are we supposed to do in this case? Now, I think this, to be honest, is a problem which has not been rigorously solved yet. And this is so much true that the two current operational interplanetary systems, the one of the University of Pisa, and the one of NASA, are not doing the same thing, which actually implies not that one is right, the other wrong, but we neither of us knows exactly what to do. So the JPL uses a strange linearity control to decide whether you can accept the probability integral even if it's done with the line of variation here, the earth is there, and then you compute the PDF in a point where it is quite far. You make an integral where the probability is low. It's clear that these are going to be virtual impacts with low probability. But are they legitimate? We at NeoDis try to apply a more rigorous principle, but not necessarily do it right, that we need an explicit VI representative. A VI representative is one initial condition which actually leads to an impact. We refuse to publish the existence of VI which cannot exhibit one action orbit we compute at which impacts. To do this, if the orbit we obtain as a minimum distance is outside of the disk, we have to apply an additional step of differential correction, which is done more or less with radiation Newton's method, to force the solution to it there. In doing this, we increase the target function, and therefore we have to correlate the probability density. Now, this is a very tricky question. I'm not going to explain this. So let me show you what the result is. The result is something like this. I'm, of course, showing you the NeoDis system. Actually, I could show you even 3 separate websites. This NeoDis system is at the server of the University of Pisa. A copy of the information from NeoDis is available through the SSA portal at the NeoCC, which is the place we're going to visit this afternoon. For the moment, this is just a copy of what is computed in Pisa, and in a comparatively short time, okay, you know, I think the Space Agency, we say should be 2016, but I'm not that sure about the date. At some point in the future, the computation will be all done in the place we are going to visit this afternoon. This system will be moved there and will become an operational visa system, which practical term means I can retire. There is a deadline. I have to retire by 2018. So please don't waste time. And the other one is, of course, a JPL. Okay, these are the websites. Sorry, I forgot the one of the ESA, but we will learn this after. Okay, let me show you. Okay, just quickly. This is an example of risk file, a bit simplified. Now, this is an example in which the width is terrible. Okay? So, as an example, I have a distance from the center of the Earth is 1300 radius of the Earth plus or minus 1365. That means the Earth cross-section is very far from the LOV, but a distance which corresponds more or less to 1 sigma. So the decrease of PDF is not that much. Still, the impact probability is very low, 1 part in a billion, more or less. However, if there was an impact, the impact would be 300,000 megatons, because this is a multi-kilometer asteroid. Okay, so even if probability is very low, this event is not completely negative. And according to our interpretation, it's worth telling. So this is an example of two-dimensional probability computation. This is a one-dimensional probability computation. Please note that the column width is essentially 0, and therefore this must be within. This is the distance in radius of the Earth, but we have to take into account the impact parameter, which is more than 1. So these are cases in which the log actually enters the case. Just one notation, and then I finish. This page was prepared in 2011, and I wrote this comment. This should be recovered in 2011 or 2012, but the apparent magnitude is 26. Okay, and then the question will be decided. We remove this aspect from the list. In 2014, I know this has not been recovered. I recently learned that Marco Micheli. Marco Micheli actually tried to recover this object and did not succeed because making an observation magnitude 26 in a big telescope is far from trivial. So this is still in the list. Okay, let's finish here. I will slowly